Well, let's now look at some of the methods used to control or at least mitigate the effects of power plant pollutants. First, we'll consider flue gas. The actual limits set on flue gas contaminants may vary between different localities, states, and countries. This table shows typical limits set for large modern power plants in North America. The emission of sulfur dioxide must be kept below an average rate of 2.5 pounds for each million BTU burned. In metric units, this is given as 1.075 kilograms per million kilojoules. For NOx emissions, the limit is set at 0.5 pounds per million BTU. The emission of particulates is limited to 0.1 pound per million BTU annual average. Another check on particulates is the measurement of opacity, here limited to 20% as an average. Other units of measurement may be used for flue gas pollutants. For example, in Europe, SO2 limits are set between 400 and 2,000 milligrams of SO2 for each cubic meter of flue gas. This is based on excess oxygen of 6% in flue gas. In operating the power plant, we find that SOx and NOx are usually measured in terms of ppm, that is, parts per million in the flue gas. For example, the NOx limit of 0.5 pounds per million BTU would be in the order of 175 ppm, depending on the precise amount of excess air being used. But this is enough about target values. How do we actually control the emissions? Well, first, let's take a look at particulate matter, which mainly consists of fly ash and perhaps some unburned carbon. In coal-fired boilers, a large amount of fly ash is produced, and the most common way to remove this from the flue gas stream is by installation of an electrostatic precipitator, ESP. An ESP, as it is known, is capable of removing 99% or more of particulate matter from the flue gas. The operation of the ESP depends upon electrostatic principles. The flue gas is forced to pass between electrodes, which are charged at a DC voltage of about 50,000 volts. This high voltage causes electrons to flow from the negative electrode through the flue gas to the positive electrode, which is grounded. The resultant electrostatic charge on the dust particles causes them to collect on the positive electrode, which is actually built in the form of a large plate known as the collector. Multiple collector plates are built in line with the gas flow and fixed solidly to the frame and outer box, which are all grounded. The negative electrodes, often known as discharge electrodes, are located between the collector plates in the gas passage. The high-voltage DC supply is obtained from transformer rectifier units, which are usually mounted on top of the precipitator. At frequent intervals, the plates and electrodes are mechanically wrapped so that the removed dust falls off into the collection hoppers below. The ash hoppers are not designed for storage, therefore the ash must be removed almost on a continuous basis. The main problems causing loss of collection efficiency in a precipitator are high resistivity of the fly ash as a result of burning low-sulfur coal, the existence of very small particulates below 0.3 microns in diameter. These problems can be overcome by installing a fabric filter instead of the ESP. The fabric filter simply blocks the passage of particulates and therefore is not affected at all by the resistivity of the fly ash. In fact, its efficiency of particulate removal is greater even than the ESP. Actually, it is not so much the fabric itself which blocks the passage of particulates, rather it is the layer of ash cake which builds up on the surface. The filter material is arranged in the form of a very large number of long bags, which are replaceable. The inlet gas flows upwards on the inside of the bag and passes through the fabric. As the inside of the bag becomes plugged, the pressure drop increases and the bag is cleaned by mechanical shakers. Means are provided to isolate sections of the filter so as to provide cleaning of some bags while the remainder of the filter continues in service. The pressure drop across the fabric filter, or baghouse filter as it is known, is quite high, about 6 inches water gauge, as compared to 0.5 inches for the precipitator. This means that larger ID fans are required. One important point to know is that the fabric filter is not suitable for use with oil-fired burners. This is because the sticky nature of the particulates, in this case, makes cleaning of the filter bags extremely difficult. Well, now, let's move on to take a look at flue gas desulfurization. Of course, the most simple way to reduce the sulfur content in the flue gas would be to purchase a fuel with 0 or very little sulfur content. Unfortunately, this is quite difficult to arrange and also quite expensive. So we are left with the problem of removing the sulfur from the flue gas stream. This is done by applying a chemical reagent. The most common reagents in use today are lime and limestone. The main ingredient in lime or limestone is calcium. When this mixes with SO2, it forms calcium sulfite in the form of solid particles, which can then be removed from the gas stream. Various methods are used to bring the reagent into contact with the flue gas so as to allow SO2 absorption to take place. In the dry method, the lime as a fine dust is blown into the flue gas stream at various injection points. The particles of lime pass along with the flue gas and attach themselves to the fly ash. Reaction with the SO2 takes place to form calcium sulfite, and this solid particulate is captured along with the fly ash in the precipitator or baghouse filter. Although this system is relatively simple, its absorption process is not very efficient, so the consumption of reagent lime is extremely high. However, this system may be utilized on small boilers if the target for SO2 removal is limited to about 60%. The most common type of FGD system installed today uses a scrubber, that is the wet limestone process. The essential feature of this process is that the reagent is mixed with water and the resultant slurry is injected into the flue gas stream. The chemical reaction takes place in a specially designed absorption tower. The tower is located after the precipitator so as to eliminate interference in the chemical reaction from some of the constituents in the fly ash. Of course, the ID fan and perhaps additional booster fans must be designed to cope with the pressure drop across the tower. As the flue gas flows through the absorber, it mixes intimately with the calcium spray, and SO2 is extracted from the gas. This is absorbed into the liquid, forming a calcium sulfite slurry at the bottom of the tower. The heaviest concentration of this slurry is continuously removed and processed. In most systems, this waste slurry is dewatered, with the liquid being recycled back to the FGD system. The remaining calcium sulfite sludge is then chemically stabilized and packed into a landfill on site. In many locations, the calcium sulfite sludge is converted into calcium sulfate by oxidation, and this is then used to make gypsum for the production of wallboard, that is a common construction material. Clearly, we are only dealing here with the fundamentals of FGD. The subject is demonstrated in much greater detail in some of our other programs, such as environmental protection control. The subject of NOx control is also dealt with in that training program. The reduction of NOx in flue gas is generally achieved by modifying the technique and control of combustion. The main objective of low NOx techniques is to slow down the rate of combustion. This reduces the temperature of the flame, with consequent reduction in the reaction between nitrogen and oxygen to form NOx. One way to achieve this is by reduction of excess air, but as we know, this may result in incomplete combustion. To overcome this, special low NOx burners are installed. These are designed to allow far more precise control over air and fuel distribution to each individual burner. Over-fire air is often added at a higher level in the furnace to help complete combustion from low NOx burners. Another technique is to use gas recirculation, similar to the arrangement for temperature control mentioned earlier. In order for these low NOx techniques to be successful, the boiler instrumentation and control system must be more complex than on earlier boilers. Precision and reliability are vital. Where emission limits are extremely tight, a chemical method is sometimes used to remove NOx from the flue gas. One method is to inject ammonia into the gas stream. When temperature conditions are right, about 1600 degrees Fahrenheit, the ammonia reacts with the NOx to produce water vapor and nitrogen, which passes harmlessly up the chimney. This process is known as selective reduction. Because of the need for high temperatures in order to ensure good reaction, the ammonia injection nozzles must be located in the superheater or reheater zone, an inconvenient location. To overcome this problem, a catalyst reactor may be fitted into the gas stream, usually after the economizer, and this allows the NOx absorption to take place at lower temperatures, say 600 to 750 degrees Fahrenheit, or about 400 degrees Celsius. This system is known as SCR, catalytic reduction. Let's now turn our attention to the cleanup required for liquid effluent. Typical limits set on discharge effluents indicate that suspended solids should be limited to an average value of 30 ppm and 100 ppm maximum. The pH value should be between 6 and 9. Oil and grease must be limited to 20 ppm maximum. The residual chlorine must be kept below 0.2 ppm maximum. In order to comply with these limits, it is necessary to remove offending solid material from the effluent, and this is done usually by clarification and/or filtration. Most of the solid material is removed and must in turn be buried in a certified landfill site. Before the final clean effluent is discharged into the river or lake, the pH will be corrected by the addition of caustic or acid. One particular nasty effluent has been addressed in the regulations, and that is the seepage of rainwater down through coal piles or ash piles. This water, taking with it contaminants, some which may be hazardous, percolates down through the earth. There it may find its way into the natural groundwater, which is often used for drinking by animals and people. Nowadays, it is necessary to install an impervious liner, usually of heavy plastic, below any of these areas, including the ash pond. Stormwater runoff must be collected and treated to remove solids. A liner is also required for the landfill area where solid waste is eventually laid to rest. In fact, there are definite rules and regulations which govern the construction and operation of a certified landfill site. Now, in these last two segments, we've endeavored to briefly outline some of the environmental problems that face us in operating a fossil-fired power plant.